Hello guys, hello everybody, and today we are going to learn about a new topic, that is Venturi meter. All right. So what is a Venturi meter? It's just a device that is used to measure the flow, measure the pressure of a liquid in different cross sections. All right. So it's also used to measure the velocity, and it is based on Bernoulli's theorem. So this is the application of Bernoulli's theorem. Venturi meter is an application of Bernoulli's theorem. So first of all, I would like to explain this diagram to you all. First of all, we have a flow in. So we have the fluid flowing in this direction through this opening. This is the main pipe with diameter d1, right? So this is the main pipe with diameter d1, and fluid is flowing in this direction. And after this, we have this convergent cone. All right. So this part is the converging cone that we have. That means now the cone converges and it reaches up to this point, right? So you have the converging cone here, and then we have the small throat section over here, in which we have the small diameter, that is d2, and then we have the diverging cone, and then again the same diameter of the pipe is reached, right? So we have initial diameter d1, final diameter d1. We reached the diameter of d2 in middle by the converging effect. Now this is just this upper portion is just a simple pipe with a converging and a constant line where we have a constant diameter, and then again diverging, and then again we had this constant diameter, right? So we had d1 here, we had d1 here, and we have d2 over here, and this is the converging part that you should know, and this is the diverging portion of this diagram. And now, after we understand this thing, now we need to understand a little bit about this YouTube manometer that is present over here. So you can see there is a YouTube manometer that is present over here. Now, what does this YouTube manometer do? The YouTube manometer is actually used for measuring the pressure. So this is the differential YouTube manometer. We have this one fluid over here, all right? So this fluid is a manometric fluid inside of this. And then we have the fluid in diameter d1. So now we are measuring the pressure of diameter d1, and then we are measuring the pressure of diameter d2. Now what does your common sense say? All right, we have already read continuity equations. We know what is continuity equations. We know everything about that. Then I would like you to ask, what does the common sense say here? Will the pressure in this section be more, or will the pressure in this section be more? Well, by figure, we are clearly we have clearly seen that the pressure in this section is high, because the manometric fluid is pushed in more depth in this region than in this region. The manometric fluid is rising above this datum line in this region, while it has raised to this more downwards. That means the pressure in this region should be high. But why does that happen? It happens because you know that when a fluid of velocity v1 flows through a diameter of d1, then it has the pressure p1, right? It has the pressure p1. Now suddenly, if the diameter d2 is less than diameter d1, then what happens is this velocity now increases. All right, so now v1 changes to v2, where v2 is greater than v1. This is by following the continuity equation. And if you look at Bernoulli's theorem now, Bernoulli's theorem states that the total energy of the body is constant, fluid flow is constant. So if the total energy of the fluid flow is constant, when the velocity increases, the pressure must decrease. So in this region where it has smaller cross section, the velocity is high and the pressure is low. So therefore you can see that the manometric fluid is quite high on scale as compared to here, right? So this is all about our learning up to now. Now I would like to look at the derivation portion, some calculations of this particular thing. We are going to calculate the velocity, then the flow rate, and then we are going to calculate the flow rate, and we are going to calculate the coefficient of discharge, right, in this particular figure, right? So let's start with our derivation portion. So first of all, I would like to write solution. So since we are dealing with Bernoulli's theorem here, I would like to start with the Bernoulli's theorem. That is, first of all, I will apply Bernoulli's theorem in this portion of the tube. So the Bernoulli's theorem in this portion of the tube can be correspondingly written as P1 by P1 by rho z plus v square by 2 z plus z equals to constant. We have velocity 1, all right, and then this region. So this is for region 1, and now we go on to region 2. So what is region 2? We get P2 by rho z plus v2 square by 2 z plus z equals to c. So we have these two corresponding regions over here. All right, now we can say that the energy is constant. We learned it, and that's the main assumption of Bernoulli's theorem. So now if we say the energy is constant, we can write P1 by rho z plus v1 square by 2z plus z equals to P2 by rho z plus v2 square by 2z plus z. Now what is z? So z is the potential energy per unit mass. Now if you say this is in a straight line at the same distance from, so let's say that we had the ground, that is the ground over here, then you can see that the structure, the different cross sections, that means this section and this section is at an equal distance from the ground. So therefore this is horizontal, so there is no change in potential energy. We can safely exclude these two terms from the equation, right? And now our equation, if I rearrange it, I can write as P1 by rho z minus P2 by rho z equals to V2 square minus V1 square by 2 times of z. Now we are going to write this equation in terms of the continuity equation, and we are going to write this equation in terms of V2. So we are going to calculate the value of V2 from this particular expression. In the previous expression, in the continuity equation, we did not deal with the pressure, but here we are also dealing with pressure. So the velocity is a little bit different from what we assumed in the continuity equation, because we only use the area relationship, but it is not only related to area, but it is also related to pressure. All right. So now we can use the continuity equation to find the velocity over here as compared to the velocity over here. So now we can calculate the velocity, right? If we know V1, so we know A1 V1 equals to A2 V2. So if we know V1, we can write V1 equals to, we can write V1 equals to A2 V2 divided by A1. And also this term is also known as pressure head. All right, so this is also known as pressure head, and we can write this as the V2 is just as it is. Then we can write this as A2 square V2 square by A1 square, and then we can just multiply this by 1 by 2z. All right, now we can write this as h, and we can write V2 square as common, and then we can write A1 square minus A2 square divided by A1 square, and then we can write 1 by 2z, and then we can again write this as 2zh, all right, equals to V2 square. Then we can write A1 square minus A2 square divided by A1 square. Now we can write V2 as root under 2zh. All right, we can write V2 as root under 2zh, and then root under 2zh A1 divided by root under A1 square minus A2 square. All right, So this is what we get. This is, I'm sorry. So this is what we get by writing all of these expressions. So this is the final result. From this way we can calculate V2. All right. So this is the derivation that we do in this Venturi meter. Now there is another thing. This H. So what is this value of H? Although we can calculate the value of H by this method, but it is always not convenient. For example, to find the pressures, because how do you find the pressure P1 and P2? Well, in order to do that, you can directly derive this formula, that is H. So all right, so H. So how do you derive this formula? Well, I'll give you a little bit of idea on how you should derive this formula. First of all, you know this is the line, so the pressure at this region will be the density of fluid. So let's say that you have the, let's say we do with the specific gravity, right? So let's say the specific gravity of this liquid PSL times, all right, SL times the density of water is into Z. All right, so this gives you the H. So rho ZH gives you the pressure at point A in this side, that is in the one side, and in the second side you can get the pressure here by writing the expression. You can write specific gravity, that is of liquid, times rho of water times Z, times you get this much distance. So now if you consider the total distance, all right, to be H, so you get here H minus X. Well, the thing is that we nearly consider this line as the baseline for measuring the distance. So if this is H, then the pressure from this tube up to this point is H, and from this point to this point is we get H minus X. And the pressure for this much section, that is for this section X, where we have the manometric fluid, we write the manometric fluid to be S naught. All right. All right, so let's say the manometric fluid to be x naught X times Z times rho of water. And now if you like solve this equation to find the value of H, you'd get the value of H, all right, you'd get the value of H to be 1 minus, right, X times 1 minus S by SL by S naught. So this is what you get if you really try to calculate the value of H, all right. So this is the general expression. Now you guys may be asking this question. So what is S naught and what is SL? So actually we have changed the diagrams. All right. So this should be actually S naught and this should be actually SL. So this is the fluid. That is, now this formula is used if S naught by SL is less than 1, right? So this formula is used, and if it is greater than 1, we can write S naught SL minus 1. That is, we can write that S naught is greater than SL. So only if we have S naught is greater than SL. I hope you understand what is S naught. S naught is the manometric fluid, the density of the manometric fluid, and SL is the density of the liquid that is flowing through the pipe. All right, so this much is the discussion for today, and then, all right, so and then after you know this, you have also another term here, that is the flow rate. So flow rate, what is flow rate? It's the mass flow uh, per unit time. All right, so it's a mass flow per unit time. So how do you calculate flow rate? So in order to calculate the flow rate, you know it is A2 times V2. And how it is so? Because you can write like A2 times, now velocity can be written as distance by time taken, and this value can be written as volume. Now if you just ignore the density for certain now, because the density is the same for a flowing liquid, then this is the flow rate of the flowing liquid. And now this flow rate, all right, this flow rate can be written as, the value of V2 can be replaced in the flow rate, that is root under 2gh A1 divided by root under, we can write A1 square plus A1 square minus A2 square. So we can write A1 square minus A2 square, and then we can write this as flow rate. Now if you want to calculate the actual flow rate, you can multiply this by the coefficient all right. So this is called as a coefficient of discharge, and its value is always less than 1, all right. So if you want the actual flow rate, you can write coefficient of discharge times A2 times, all right, root under 2gh A1 by root under A1 square minus A2 square. So this is the expression. Now, I hope we covered everything that we should learn in Venturi meter, and after we learn this, we can do all the numericals that are associated with Venturi meter. And this is the application of Bernoulli's theorem that we had just learned previously in our previous scenarios. All right. So this much for today. Thank you, everybody.